let's derive an expression for the Fermi momentum. The Fermi momentum is the maximum momentum a particle has if it's part of a gas that's degenerate. Or more precisely, it's the maximum momentum a particle would have if the temperature is 0 kelvins, and it only applies to fermions. Because bosons at 0 Kelvin, all bosons will go to the lowest energy state. But at 0 Kelvin, all fermions cannot go to the lowest energy state because no two fermions can occupy the same state. So even at 0 Kelvin, higher energy states are occupied. And the Fermi momentum is just what is the highest momentum state, or in the Fermi energies, just what's the highest energy state that's occupied at 0 Kelvin. We will make the following assumptions. First, since we have a gas of fermions, we're going to assume that the fermions have a fermion distribution function, f of e, where f of e is basically the fraction of states with energy E that are occupied by fermions. And as you can see, that's 1 over e to the energy minus chemical potential over kT plus 1. And that was derived in a previous video. We also need the density of states, g of p dp. That's the number of states with momentum between p and p plus dp. And that's just g sub s, which is the number of spin states, times 4 pi volume over Planck constant cubed, times the momentum squared times dp. Then we also assume that the number of particles, the total number of particles present, is the integral from 0 to infinity of f of p g of p dp. And that should make sense because f of p is the fraction of states with momentum p that actually have particles. And g of p is the number of states with momentum p that have, that's just period. So if you multiply the total number of states with momentum p by the fraction of states with momentum p that have particles, you'll get the total number of particles that have momentum p. And then if you just sum that up, you'll get the total number of particles. And the sum becomes an integral. Because we're assuming it has continuous momentum. Anyway, a little n is the number density, so it's just the total number per volume, number of fermions per unit volume. And we assume that fermions are non-relativistic, so we can write the energy as p squared over 2m, or momentum squared over twice the mass. Finally, we care about the limit where the temperature is 0 Kelvin. So those are our assumptions. So what we want to do is we want to find what the distribution function is at 0 Kelvin. So write the distribution function at the top of the screen. It's just the fermion distribution function. That just basically means that the fraction of states with energy E that have a fermion is 1 over E to the energy minus the chemical potential over kT plus 1. We care about the limit that the temperature goes to 0, so take the limit that the temperature goes to 0. So as you can see, when the temperature goes to 0, we need to worry about what is the exponential of E minus mu over kT, because that basically becomes e to the e minus mu over 0. And e minus mu over 0 can either be positive infinity or negative infinity. If e minus mu is negative, then e minus mu over 0 is negative infinity. And if e minus mu is positive, then e minus mu over 0 is positive infinity. So e minus mu is negative when e is less than mu. And so when e is less than mu, the distribution function becomes 1 over e to the negative infinity plus 1. And when e is greater than mu, e minus mu is positive, so e to the positive infinity is infinity. And 1 over infinity is 0. But the important thing is that when the energy is greater than the chemical potential, the distribution function becomes 1 over e to the infinity plus 1. So 1 over e to the infinity plus 1 is 1 over infinity plus 1, which is 1 over infinity, which is 0. So the distribution function is 0 when e is greater than mu. And when e is less than mu, the distribution function is 1 over e to the negative infinity plus 1. But e to the negative infinity is 0, so it's 1 over 1, or just 1. So when the energy is less than the chemical potential, the distribution function is 1. So all that means is that the fraction of states with energy greater than mu that are occupied is 0. So no states with energy greater than the chemical potential are occupied when the temperature is 0 Kelvin. And all states with energy less than mu are occupied because the distribution function is 1 if the energy is less than mu. So we call the special energy E equals mu the Fermi energy. So we define the Fermi energy E sub F as mu, and the momentum at the Fermi energy is called the Fermi momentum. And since we're dealing with non-relativistic particles, the Fermi energy is the Fermi momentum squared over twice the mass. And I've drawn on the screen an example of a system. The yellow dashes are states, and red dots mean that particles are occupying that state. And I've drawn it so that the yellow dashes that are drawn higher up have higher energy. So all the yellow dashes below the Fermi energy have red dots because they're occupied at 0 Kelvin. Now let's derive the Fermi energy, or Fermi momentum. So first, write the expression for the total number of particles. It's the integral from 0 to infinity, distribution function times the density of states. But the distribution function is 0 if the momentum is greater than the Fermi momentum, and it's 1 if the momentum is less than the Fermi momentum. So the integral from 0 to infinity of f of p, g of p dp, is just the integral from 0 to p sub f, g of p dp. And we already agreed that the integral, or that g of p dp, the density of states, is g sub s 4 pi v over h cubed p squared dp. And so 4 pi volume over h cubed times g sub s is a constant, so pull out the integral, and we need to integrate p squared from 0 to p sub f. And of course that's just 1/3 p sub f cubed. So combine everything together to get that, and then solve for p sub f cubed to get that p sub f cubed equals 3h cubed n over 4 pi g sub s v. Take the cubed root of both sides and define the number density to be the total number divided by the volume. So we get that the Fermi momentum is Planck's constant times the cubed root of 3n over 4 pi g sub s, which means that if the temperature is 0 Kelvin, the highest momentum state that is occupied will have momentum h times the cubed root of 3n over 4 pi g sub s.